Alright, welcome back. I'm going to be continuing with the Cosmic Python series. I kind of had my doubts last time about this series. It's just a lot of what I've been reading is kind of over my head, or just not relevant to the things I want to do. But we'll keep giving it a shot here. So this is Section 3, a brief interlude on coupling and abstractions. Allow us a brief digression on the subject of abstractions, dear reader. We've talked about abstractions quite a lot. The repository pattern is an abstraction over permanent storage, for example. But what makes a good abstraction? What do we want from abstractions, and how do they relate to testing? The code for this chapter is in the Chapter 3 Abstractions branch on GitHub. I don't see it. A key theme in this book, hidden among the fancy patterns, is that we can use simple abstractions to hide messy details. When we're writing code for fun or in a kata, we get to play with ideas freely, hammering things out and refactoring aggressively. In a large-scale system, though, we become constrained by the decisions made elsewhere in the system. When we're unable to change component A for fear of breaking component B, we say that the components have become coupled. Locally, coupling is a good thing. It's a sign that our code is working together, each component supporting the others, all of them fitting in place like gears of a watch. In jargon, so that's coupling. So a watch, all the components are coupled. In jargon, we say this works when there is a high cohesion between the coupled elements. Globally, coupling is a nuisance. It increases the risk and the cost of changing our code, sometimes to the point where we feel unable to make any changes at all. This is the problem with the ball of mud pattern. As the application grows, if we're unable to prevent coupling between elements that have no cohesion, that coupling increases superlinearly until we are no longer able to effectively change our systems. We can reduce the degree of coupling within a system, lots of coupling, by abstracting away the details, less coupling. Okay, so these are two graphics. The first one shows if we have lots of coupling, and coupling are components that are basically like coupled together. So you couldn't change system A without changing system B unless you had less coupling, as we can see here. Now you have an abstraction, so you can change system A and it won't affect system B because both of those systems are dependent on an abstraction and not on each other. In both diagrams, we have a pair of subsystems with one dependent on the other. In lots of coupling, there is a high degree of coupling between the two. The number of arrows indicates lots of kinds of dependencies between the two. If we need to change system B, there's a good chance that the change will ripple through to system A. In less coupling, though, we have reduced the degree of coupling by inserting a new, simpler abstraction. Because it is simpler, system A has fewer kinds of dependencies on the abstraction. The abstraction serves to protect us from change by hiding away the complex details of whatever system B does. We can change the arrows on the right without changing the ones on the left. Abstracting state aids testability. Let's see an example. Imagine we want to write code for synchronizing two file directories, which we'll call the source and the destination. If a file exists in the source but not in the destination, copy the file over. If a file exists in the source but has a different name than in the destination, rename the destination file to match. If a file exists in the destination but not in the source, remove it. Our first and third requirements are simple enough. We can just compare two lists of paths. Our second is trickier though. To detect renames, we'll have to inspect the contents of files. For this, we can use a hashing function like MD5 or SHA-1. The code to generate a SHA-1 hash from a file is simple enough. And here it is, hashing a file. There we go. Oh, this is actually Okay. Now we need to write the bit that makes decisions about what to do, the business logic, if you will. I actually do want to save this because I might have need to hash a file. So we're going to do yes. So we're going to copy this, and then we're going to add oops, I did a copy. Okay, so now we'll paste this in. Oh, I've got to go to edit mode. There you go. Okay, now I can now I can paste this in. And put this at the end. There we go. Copy that. Perfect. So now I can add a note. How? Let's do a simple way to hash a file. Show one hash a file. Now we need to write the bit that makes decisions about what to do, the business logic, if you will. Oh, one thing I forgot to do is move the current down to the previous. When we have to tackle a problem from first principles, we usually try to write a simple implementation and then refactor toward better design. We'll use this approach throughout the book because it's how we write code in the real world. Start with a solution to the smallest part of the problem and then iteratively make the solution richer and better designed. Our first hackish approach looks something like this. So this, I think this is for, yeah, this is for, oh, I could probably have, well, let's just keep, I just want to read as much of this as possible. Well, you know what, this is easy. This I am gonna type out because this doesn't depend on anything else. We're just gonna type this out in the style of the book Learn Python the Hard Way, where you just type things out without worrying about whether you understand it or not. I find that's generally an okay way to learn. It's better than doing nothing, but sometimes it's similar to doing nothing if it's too far beyond you. You definitely, one thing I always try to do is find the balance in learning where you're not completely bored, it's all super easy, but it's not all over your head. You've got to find a level where you're challenged. You're not getting everything the first time, but if you put effort into it, you can eventually figure it out. You've got to find kind of a balance between things that are too hard and things that are not hard enough. And if something's too hard, you're going to get frustrated. If it's too easy, you're going to get bored. So you got to balance that boredom and frustration, and you've got to prevent yourself from, keep yourself focused without getting absolutely frustrated. All right, this is not okay. It is opening now. Does it open to where I want it to open, though? That is the question. Yep, so it's open there. It's pretty nasty, but that is, I guess, okay for now. Yeah, it's really slow. It's much slower than usual. Normally it's not this slow. Okay, but yeah, let's follow along with this example. So they're calling this sync.py. Let's call it that. Okay, and then we'll close this, close that, and then we'll just type out the whole thing and go through it. So I've never heard of this shutule. I want to learn more about that eventually. My computer is actually like breaking. It's like the battery is swelling on it, so like the space bar is like not working very well now. Yeah, this space key sucks. I have an external keyboard that I'll plug in somewhere. At least I thought I did. Oh, it's right here. Alright, so I will use this instead. Alright. So, yep, now I can get a space bar that actually works. Much better. Oh, but now the A key doesn't work on this. Well, shoot. I mean, I have one more external keyboard, but it's kind of like a novelty keyboard I have. I don't have any working keyboards anymore. I'm gonna need to buy a new external keyboard. Yeah, I'm gonna need to buy a new keyboard. This is just not working. Okay, so I think I'm not sure what this part of the code is doing. Minus fn, so we're minusing something. So we're doing some sort of math there. Not exactly sure what that's all about. Yeah, I'll probably get a mouse as well. I kind of want to just like use this time to like shop for my new gear, but like I don't think that's what I want to have on this channel. Is just me like shopping for stuff. I mean, I guess if it's computer equipment. Okay, so then we've got another for loop underneath this one for every file that appears in source but not target. Copy the file to the target. All right, so fantastic. We have some code and it looks okay, but before we run it on our hard drive, maybe we should test it. How do we go about testing this sort of thing? So we can do that by using the Python tests PyTests module, which recognizes files with this prefix here, test_. So we'll make a file with that prefix. And the rest of the file will be named the same as the file we just made. All right, and now we'll make a few functions that'll be the test. The first thing we're going to do is we're going to test when a file exists in the source but not in the destination. So we'll make a function named def test when a file exists in the source but not the destination. Try source equals temp. The temp dest equals temp file dot temp. Now I don't know what this mkd temp method is. I'm really doubtful that this is going to work. But I'll just give it a try anyway. I'll just type out exactly what I see here, and once I run it and it doesn't work, we'll get back some error messages. Be able to figure out more easier at that time what is going wrong. Now there's no try except here, there's a try finally. From what I understand, you can have a try statement that has an except clause, and then if the code in the try fails, there's an error, a Python error triggered. Then it will run the code in the except clause, but if it succeeds, it will skip the code in the except clause. So it looks like what a finally clause does is it runs whether there was an error or not. So if there's an error in this try block, let's say it errors on line 9, it'll go down to line 8, try to run line 9, have an error, but now that there's a finally statement instead of an except statement, it will move on and run the finally code instead of just not executing this if this were an except statement. Oh. Okay, here I'm confused. I didn't know you could divide something by a string like that. I'm just curious about that. Let me try that. Yeah, let's do a sudo apt install IPython. Oh, a sudo, not a sudo. So sudo apt install Python. Sometimes it's easier to just type it all out again. There we go. %. Alright, that's going to be a while. I'll try to keep typing while that's going. Oh, but that's making everything go really slow. Oh my god. This is rough. Alright, so I've got my test file. I've got IPython installed now, so I'm going to try dividing something by a string to see if that works. Let's divide an integer by a string. So let's see what 10 divided by hello is. It is unsupported operand type. Okay, well let's see what world divided by hello is. Unsupported operand. Okay, yeah, so I'm not sure if this operand is gonna work. Yeah, I don't know what's going on there. Alright, well, let's just continue. Wowzers, that's a lot of setup for two simple cases. The problem is that our domain logic, figure out the difference between two directories, is tightly coupled to the I/O code. And we can't run our difference algorithm without calling the pathlib shutil, and hashlib modules. And the trouble is, even with our current requirements, we haven't written enough tests. The current implementation has several bugs. The shutil.move is wrong, for example. Shutil.move. Shutil.move. Oh, here we go. So if there's a file in the target that has a different path in the source, move it to the correct path. I don't see how that's incorrect. Oh, is this meant to be source instead of dest? No. Yeah, I don't know how that's incorrect. Getting decent coverage and revealing these bugs means writing more tests, but if they're all as unwieldy as the preceding ones, that's going to get real painful real quickly. On top of that, our code isn't very extensible. Imagine trying to implement a --dry-run flag that gets our code to just print out what it's going to do rather than actually do it. Or what if we wanted to sync to a remote server or to cloud storage? Our high-level code is coupled to low-level details, and it's making life hard. As the scenarios we consider get more complex, our tests will get more unwieldy. We can definitely refactor these tests. Some of the cleanup could go into PyTest fixtures, for example. But as long as we're doing file system operations, they're going to stay slow and be hard to read and write. Choosing the right abstractions. What could we do to rewrite our code to make it more testable? First, we need to think about what our code needs from the file system. Reading through the code, we can see that 3 distinct things are happening, and can think of these as 3 distinct responsibilities that the code has. The first responsibility, we interrogate the file system by using os.walk and determine hashes for a series of paths. This is similar in both the source and destination cases. Responsibility number 2, we decide whether a file is new, renamed, or redundant. Number 3, we copy, move, or delete files to match the source. Remember that we want to find simplifying abstractions for each of these responsibilities. That will let us hide the messy details so we can focus on the interesting logic. Note, in this chapter we're refactoring some gnarly code into a more testable structure by identifying the separate tasks that need to be done and giving each task to a clearly defined actor along similar lines to the DuckDuckGo example. For steps 1 and 2, we've already intuitively started using an abstraction, a dictionary of hashes to paths. You may already have been thinking, but why not build up a dictionary for the destination folder as well as the source, and then we just compare 2 dicts? That seems like a nice way to abstract the current state of the file system. But what about moving from step 2 to step 3? How can we abstract out the actual move, copy, delete file system interaction? We'll apply a trick here that we'll employ on a grand scale later in the book. We're going to separate what we want to do from how to do it. We're going to make our program output a list of commands that look like this. Copy source path this path, move old new. Now we could write tests that just use 2 file system dicts as inputs, and we would expect lists of tuples of strings representing actions as outputs. Instead of saying, given this actual file system, when I run my function, check what actions have happened, we say, given this abstraction of a file system, what abstraction of a file system actions will happen. Okay, so it looks like we've got 3 dots here, which means there's more code than is shown on here. So I'm not sure if I can type this all out. It looks like maybe. Okay, so we're modifying the tests. So I'm going to close this file and focus on the one we're modifying. So it looks like they're making some changes here. The expected actions. Yeah, I guess I'm not sure what they're doing here. Alright, implementing our chosen abstractions. That's all very well, but how do we actually write those new tests, and how do we change our implementation to make it all work. Our goal is to isolate the clever part of our system and to be able to test it thoroughly without needing to set up a real file system. We'll create a core of code that has no dependencies on external state, and then see how it responds when we give it input from the outside world. This kind of approach was characterized by Gary Bernhardt as Functional Core Imperative Shell, or FCIS. Let's start off by splitting the code to separate the stateful parts from the logic. And our top level function will contain almost no logic at all. It's just an imperative series of steps: gather inputs, call our logic, apply outputs. Here's the first function we